Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome back to SIC2006. Today we are going to proceed with our next topic. Before that, let's recap what we have covered so far. So we have discussed on the spin properties of the nucleus of an atom. We talk on the energies of the nuclei when you apply the magnetic field. Talk on some NMR experiments, the setup, and from the video that you've watched, the RSC video. We talk on the population of energy levels, talk about the two relaxation processes, the spectral width, and the last lecture was on chemical shift. Well, today we're going to cover on spin-spin coupling. I'd like to take an example here of the ethanol NMR spectrum here, and you will notice that each of this group consists of multiple lines and these fine structures that you see here. So although that there are three functional groups in ethanol, but you see that they are actually split. You see the fine structures in the spectrum, and this fine structure is due to the interaction between the magnetic nuclei in the molecules. So there's a neighboring effect. So it's not just so you get this peak from these different functional groups, but at the same time there's effect from the neighbors. And so that gives this fine structures what we call the spin-spin coupling. And the strength of the interaction is expressed in terms of the coupling constant, labeled as J, and it is measured in hertz. Sometimes in textbook it's called indirect spin-spin coupling or indirect dipole-dipole coupling. So it's actually the same as this coupling constant. Okay, and so let's consider this molecule. Now, if there is no spin-spin coupling, okay, so obviously these two hydrogens are not in the same environment. This is pretty much linked close to iodine, and this one is linked to chlorine. So if there's no spin-spin coupling, what you get is really the spectrum. But what you get instead, okay, because of the spin-spin coupling, this is what you're going to get. So clearly, it shows that there is actually interaction that's going on. And that's what we're going to talk today. Now, here's a question for you. So I don't have questions at the end of the lecture. I have questions, in between, within the lecture. So the first question is, why is the chemical shift for this hydrogen here? Why is it here and the X here? So the clue is look at the periodic table. Okay. All right, so talk about that. So let's understand this, okay? And we can understand this splitting in terms of the energy levels of the coupled system, okay? If you have a system that has two protons like the one that you see before, so say the proton A will have alpha A, beta A, that's the energy, okay? And so you have here for the proton X will have alpha X and beta X. And so when they actually combine, there are four spin states. Then you have the lowest energy, which is always the alpha. You have the alpha A, alpha X, and the highest extreme will be the beta A and beta X. So in between you have the alpha A and beta X and beta A and alpha X. And remember that alpha spin state is positive half and beta is negative half. So when there is no spin coupling, so the energy of the system, when you have this, this two proton system, is given by this equation. You have the minus h nu m, and you have the a and you have the x. Okay, and the nu a and nu x are the Lama frequencies of a and x, and ma and mx are the quantum numbers. So it's plus minus half, or plus, for both the ma and mx. Now this equation is not something which is entirely new, because really it's derived from what you have actually seen before. So let's look at the next slide and talk a little bit on that. Okay, so we've seen this equation before, and you know that the energy is equals to minus the gamma, which is a gyromagnetic ratio, and you have the quantum number h bar, which is just the Planck constant over 2 pi, and the magnetic field. Right, so if you spell out this h bar to h over 2 pi, so you will see something familiar. You have the gamma, you have the over 2 pi, you have the beta naught. Sure enough, that is actually the Lama frequency. So if you actually combine this equation 1 and 2, what you get is really that equation that you see in equation 1. So really, this is how this equation is obtained. Okay, as I said, I like to show how equations are being derived so that you can appreciate the equation even more. So this is when there's no spin-spin coupling. Okay, so how does the energy level look like? So you'll see that for the alpha A, alpha X, if you actually just plug that into this equation here, so you know that the the alpha is going to be a half, and the so this is for alpha, so that's fine. So you get here negative half h nu a minus half h nu x. So that's proven. Okay, so what this is the next thing that I want you to do. It's not a question, it's a little exercise. So now that we have the equation for alpha A, alpha X, go ahead and use this equation to just prove the equations for this, this, and this. And you should get that based on this equation. And even from there, you can actually find the delta E for all this, okay? The x1, x2, a1, and a2. Okay, find the delta E. So that's when there is no splitting. But the energy, as you can see, obviously that there's this splitting. You have this coupling going on due to the neighboring effect. So then there must be, on top of the equation, the existing equation, there is an additional term that caters the coupling constant, and this is the equation, the additional term that's added to that existing equation. So what you get is this original equation plus that additional term which has the j there. And so for j, which is a positive, a low energy is obtained when you have the two protons which have opposite spins, and if they have parallel spins, then the energy is raised. Now so here is the additional term, and these are the respective additional term for all these energy levels. So how then it will look like? So this is when there is no spin-spin coupling, but when there is a spin-spin coupling, so you see that this is raised by quarter hj, and when it's opposite spin, you have a reduction of the negative quarter hj, and so on and so forth. Okay, and So this is the equation. So go ahead and also prove this as well. So when a transition of nucleus from nucleus A from alpha to beta occurs, okay, so you have this negative half minus plus half, you have negative 1. So the spin of nucleus X will remain unchanged, okay, and so meaning that you're looking at alpha A and beta A, and the alpha X and beta alpha X, that doesn't change. So you have alpha A, beta A from beta X to beta X, that doesn't change, okay? So the other thing that I want you to prove is that find what is the energy difference. And so this is where the splitting actually comes in. So when you take the energy difference, say, for this alpha A beta X and alpha A alpha X. So you take X1, you find X2, you find the value A2 and A1. You will find that the energies of this, for example, is for the A, okay, so you find that the energy difference is h nu A plus minus half. So you can have, so because of this plus minus half, so here, so the what do you call, the resonance consists of a doublet, separated. You have this J separation center on the Lambda frequency of A. So this is actually split into two. So that's why you have this this doublet. Okay. So likewise, if you calculate for nucleus B, you will find that it will be h nu x plus minus half hj. So prove these two so that you feel that satisfaction. I also like to note that the magnitude of J is independent of the applied magnetic field. Okay, and so the separations is the same if you use a weaker or a strong magnetic field. Okay. Now, so this is just extra. So my the focus is to show you the nature of this doublet, the splitting. So via this energy diagram. So this is just extra. Okay, the coupling constant of two nuclei separated by n bonds is denoted by Nj, with subscript indicating the type of nuclei involved. So if you have 3J, K is the coupling constant between two protons separated by 3 chemical bonds. And J can take positive or negative values. So note that when you have this, the alpha A, alpha X, and beta A, beta X raised by a quarter Hj, and you have this opposite spin, it's lowered by this value. So the opposite is true if you have a negative J. Okay, so we're not going to progress further than that, but organic textbooks would usually describe this in detail. Okay, and then you have different types of, you have different names for this coupling constant. So you have the germinal coupling, which is the 2J, and you have this vicinal coupling, which is separated by 3 bonds. So this is just how the germinal will look like. So there's a separated, the coupling is separated by the 2 bonds. And if you see something like this, that's the vicinal coupling, okay, separated by 3 bonds. Okay, so that's all for today's lecture. So please, I hope you understand what is the origin of the spin coupling. So you can actually, you see that because of the energy levels, when they're splitting that, and do that, the exercise which I asked you to prove the equations. Okay, all right, so thank you, and Assalamualaikum warahmatullahi wabarakatuh.